partition is set up, make sure one machine is appointed as master. And then know that everybody is aware that the master has changed if a master changes. Those are the functions that I want from some system. Forget about Zookeeper. Everyone, please forget about Zookeeper. You keep asking what is Zookeeper. There's nobody called Zookeeper. There's a problem we want to solve. We will build Zookeeper ourselves. What is the problem that we are trying to solve? Is that clear to everybody? Master, new master selection, updating the master. Is that problem statement clear? Now let's see how we can solve it. Okay. So we say, okay, fine. Let's say there is, for now, let's assume that there is this one magic machine. And by the way, just flagging, Zookeeper is what was used in Kafka till the most recent version. In the most recent version, it is replaced by Kraft. But look, if you don't understand how Zookeeper works, you'll not understand how Kraft works. Because Kraft is just a modified functionality. So please listen carefully to understand what Zookeeper is. You can't skip and go to the 10th step in one go. All right, so let's assume that there's a magic machine. Is it fair to assume all of you know what a hash map is? Key value pair, hash map. All of you know what that is? Key value, yes? Okay. So imagine this, this machine has two kinds of hash maps. And unfortunately, I can't explain what a hash map is if you don't know hash map, because that's again a basic concept. I'm just going to assume that you know hash map. Let's say it has two different kind of hash maps, this machine. One is a proper hash map, the exact key value hash map that we know of. Let's assume Java hash map that we all know of, right? If you have used Java. But regular hash map, like it's called as dictionary in Python, hash map in Java, in C++, there is map, unordered map, that is hash map, right? So any of that. However, let's say it also has a very different kind of hash map, which is a second hash map. And the way that hash map works is, it says, look, you can't just randomly create a key and value in this hash map. It can only be created by a different machine. So a machine can say, I want to create a key and value. Now, which means key K has exactly one owner machine. So whichever machine created this key and value is the owner for this entry. And nobody other than this machine, so a different machine cannot come and modify this key or value. So nobody, the owner is the machine that creates this key and value. Nobody else can modify. They can read, but they cannot modify. And one more rule here, that owner machine is not like the permanent owner. It has to keep notifying, keep renewing the ownership. So it has to probably, let's say, for example, every 5 seconds, say that I am present here and I am the owner. If it fails to renew ownership, then this key and value, they both are deleted. The owner is gone, the entry is deleted. Okay. In key value, yes, key is unique and the value is value, right? Like you can have anything as value. Just like hash map. Remember hash map. Hash map cannot have two keys which are duplicates. You have one key and corresponding to that, one value. All right, so these are 3 rules. Now using these 3 rules, and this hash map is called as ephemeral nodes. Using this rule, we will solve the master problem, master selection problem, as well as master update problem. By the way, the same ephemeral node thing is used for multiple other things. It also used for tracking which machines are alive, which machines are dead. I will give that as a homework to you, but let's solve the master problem using this ephemeral node. These 3 rules are clear to all of you. Can I assume that nobody can go and randomly create a key value here? An external machine has to. Whichever machine creates it is the owner machine. Other machines cannot go and modify that key value pair. And if the owner machine does not renew its ownership every 5 seconds, then this key value would be deleted. So those are the 3 rules. We'll use those 3 rules to solve the master problem. Now imagine, let's say for partition X, there are these 3 machines. Let's say we have said, look, for this partition, I am reserving these 3 machines. One of these machines has to, let's call them M1, M2, and M3. One of these machines has to become the master. The other 2 have to become the slave, which means that at the time of setup, there has to be a master selection that has to happen. Now, all of these machines basically have a code for master selection, where the code says, try to go and create a key value pair in this zookeeper. Let's say the key name, hypothetically, the key name could be anything that you select, but let's say the key name is master. Whoever is able to create this key, and maybe value is your own IP address. Whoever is able to create this becomes the master. Right? Now, what happens is all of these machines have that code, which means all of these machines, the moment they get started, all of these will first go at the same time, will make a request to the zookeeper that, hey, look, I want to become the master. I want to create this entry inside zookeeper. So all 3 requests would probably reach at the same time. However, when you have a multi-threaded system, you typically, what you do is you acquire a lock. You don't want to that all 3 threads are trying to create this at the same time. That will cause race condition problem. So you acquire a lock. You say, let's say the code inside zookeeper could say, let's acquire the lock on this name, master. And inside the lock, now I will, if somebody is trying to write, now I'll try to create this entry of master to the IP address of whoever has sent this request. Now what's going to happen is, obviously, if all 3 are reaching at the same time, only one will be able to acquire the lock. Hypothetically, let's say M2 acquires the lock. M2 is able to get through. So M2 will create this entry, master, and the IP address will be of M2. So fine, this happens, successful, great. Because this was successful, the M2 will assume I am the master now. The other 2 requests for M1 and M3, they were waiting till this was done. Now M1 will acquire the lock, M1 will go in, will try to modify the entry for master, but it can't. This violates rule number 2. So zookeeper will say, look, the owner of this entry is M2. This is the owner. You are not the owner. You're also not the owner. So M1 tries to modify this entry, but it can't, it fails because it's not the owner. So M1 gets an error. And hence M1 knows I am not the owner. So now if M1 wants to know who is the owner, they can go and read the value. The value is M2. Now M1 knows that I am a slave. Next, M3 will be able to acquire the lock, but again try to modify the entry. It can't, will get an error. And hence M3 also knows that I am a slave. Master selection has happened because of this lock acquiring mechanism. Only one person will be able to write this entry. Whoever is able to write the entry becomes the master. Master selection is done. Now, problem is, how do other people know that this M2 is the master? So, I'll erase this. Imagine, let's say, there's a separate machine. Which wants to know who is the master for this particular partition. Now this machine basically can now go and read directly from here. Whatever is the value corresponding to master is the current master. So fine, this now knows that M2 is the master. If I have to do a write, I will directly send the request to M2. Now do I need to, however, keep going to zookeeper every single time? Not really. What I can do is, I can cache that, oh wait, for partition X is actually M2. But the problem is, if I have cached it, which means any request comes, I directly read from here and I directly go to M2. The problem will come whenever M2 dies, because then master will be updated and I would not know. So hence, zookeeper gives you one more functionality. It's basically called setting a watch. So on any key, any machine can set watch, which is basically like I am subscribing to any change that might happen to this particular key. Whenever this key changes, just notify me that this key has changed. I am setting a watch, which means subscribing. Every other machine will also do a very similar thing. So, which means Zookeeper internally for every, it has a value, and for every key it also has a subscriber list. So whenever this key changes, basically Zookeeper takes a loop on the subscriber list and sends a request to every single subscriber saying that, look, the key has changed. If you didn't know already, the key has changed. So please delete whatever you have in your cache whenever it changes, right? So anybody who subscribes will be in that list. Could be the slaves, could be the other machines, could be some random machine as well. Anybody can subscribe. Okay. All right. Now what is happening? Listen. So this my master is basically sending a request every 5 seconds here to the Zookeeper saying, look, I am still here and hence I am the owner. Great. Till the master is alive, it will keep sending a request every 5 seconds. It will continue to be the master. Things will run great because any machine, let's say if a request comes for a partition, it goes to this machine, the machine will be able to look at its local cache and forward the request without even going to the Zookeeper, right? So in a way, I'm saving time as well. Problem becomes, let's say if the master dies, what is going to happen? If the master is dead, then this request that was supposed to go to Zookeeper after 5 seconds